Hello. We would like to welcome you all to the presentation of a 15th Computational Archival Science Workshop of IEEE Big Data. We are here to present our paper, which is entitled as Towards Automatic Data Cleansing and Classification of Valid Historical Data, an incremental approach based on MDD. The authors are Inder OShea, Rafalesia Khan, Kira Britnich, and Tiziana Margaria. These are the outlines I'm going to discuss throughout this presentation. So, Death and Burial Data, Ireland, 1864 to 1922, DBDIRL. It's a national data-driven public history resource project in digital humanities. It uses historical data like death registration to explore the history of Ireland population and health over 1864 to 1922. For knowledge discovery, we adopt the context-free model translation system as a formalism to specify product lines to document type description. The goal is to then proceed the product line verification using context-free model checking techniques, especially the M3C model checker to ensure that they are fit to purpose. The goal is to later implement and manage the corresponding family of data models and the process in time framework to define and efficiently manage the interoperable historical data framework. The resulting hierarchy product line verification will allow our technical platform to act as a high-quality service provider for digital humanitarian research. So we were provided with a 4 million civil registration entries of Ireland death data. Sooner it's going to be a 7 million individual entries, which are handwritten documents. Here we are showing a sample of it, having 11 complex data fields, and they are all were stored in a tagged image file format. So how our project contributes to the computational archival data research in the age of big data? Well, accessing to historical civil registration data provides a unique opportunity to examine the health of population over a long time, and it determines pattern of underlying social constants, at the same time increase our understanding of the Irish people's life back then. Also, it identifies the current trends, requirements, and potential in the historical civil registration. For ensuring all this, a well-configured model-driven data record archival system needs to overcome the challenges of old record collected and recorded manually. It also needs to validate the data system and to protect the privacy and data security. So following this, DVDIRL develops efficient, flexible access mechanism to high-quality data from historical records from heterogeneous sources and makes them accessible to a wide range of reasons. Some of the state of art, we found some different types of work that relates to DVDIRL. There are some existing work about health analysis. They works with progression patterns, effect of aging. There also exists some popular World Health Organization works. They research about the study of global aging or maternal death cases. There exists some literature on cause of death analysis. They analyze the human death data and ensure the importance of civil registration, and also analyze the survival patterns and chains. But none of them reflects the model-driven development. So there exists some other works there are model-driven development-based work, which are most of the use visions and knowledge, and then there also exists some extreme model development works that works with applied robotics and then translation of user objective and probabilistic modeling, and there exists some context-free model checking for DDTs. So now I'm going to discuss about DBDIRL's data collection. So we receive a data from both structured and non-structured sources of mainly death, birth, and marriage information from Irish Genealogy website, National Archive website, coroner's records, and other miscellaneous sources. The GRO provided us a data dump as an Excel spreadsheet, and they are stored in a non-networked PC and only accessed by the project members. So now I'm going to discuss about the challenges we faced in case of data digitalization phase and how we solved them. So the main challenge was how we gonna entry the huge amount of data in time. So our project members worked really hard to make them done, and also to speed up the process. We have organized hackathon events where both undergraduate and master's students of UL helped us entering the data. The next challenge was to understanding the complex handwriting, as the records created by different registered with different styles, which needs close inspection and skill interpretation of handwriting, and also a knowledge of the domain. So we have used a map, island map from the 18th century, also a 19th century statistical nosology, a register of Dublin data, so that we can ensure we have using the proper name, the address, and also the cause of deaths, etc. And then we faced ambiguity, like the single word street was written as SST or something else, so we need to fix them, and this was done by our proposed classifiers later. So I also face some human error or some writing errors which needs to be solved by ourselves, because no machine learning or language processing tool can just guess the difference between a name Kent and Ken. So we need to go through them one by one and fix them ourselves. Also, as we receive both structured and non-structured data, we divided the 11 properties into 63 individual properties to get the proper information from each of them. Also, there was some missing data which was highlighted by our proposed classifier, which will be discussed later.
Machine transcription is a way of gathering textual data from images. So this uses machine learning algorithms to pick out textual data from images and then transcribes the words for you. However, DBD aren't used to transcribe the software. However, this required large volumes of data of the same scribe for training, as well as uploading documents to their servers for the process to work. These two issues proved troublesome, as well as the software's ability to identify handwriting of different scribes, such as the registrars and informants. So the results were varied. Related work in this area includes the Vatican Manuscript Archives and handwritten text recognition systems, which both use convolutional neural networks in picking out not only just handwriting or handwritten text, but also individual letters as opposed to words, which may be the way forward in identifying certain areas. DBD Ireland organised a hackathon in the Gloughlan Library of the University of Limerick to help with the ingestion of the civil registration of death records. Participants included 20 current master students, 3 past master students, as well as doctoral scholars and lecturers. On the right, you can see a typical TIFF file and the 11 initial data entries that come with such a file. This was expanded to 24 for the hackathon. Participants were trained by the DBD Ireland members as to the best practices for manual transcription of these records. This included the use of a 19th century medical nosology for the certified cause of death to help them in identifying within that medical domain. This gave us a total of 12 data sets, all captured into Excel spreadsheets as a result of this transcription. Upon inspection of the data captured in the Excel spreadsheets from the hackathon and other DBD members' transcription, it was determined that additional parsing could be done to get a finer layer of granularity. From this, a Java ad hoc parser was developed that expanded 24 data fields out to 63. This included natural data field expansion, such as son of a labourer was expanded to relation to be son, and occupation would be of a labourer. Ambiguity resolution, as you see on the right, in duration of illness, you could have multiple different variants of the same type. These were all standardized to be numeric into their own different columns. Additional fields were added for future research, and ability to anonymize data if required was also included into the parser. This gave us a finer granularity of our data resource, which will provide researchers with greater scope for queries. And the introduction of new data fields such as latitude allowed us the ability for potential machine learning techniques such as determining clustering within an area of a city for certain diseases, etc. This is just a continue of the data parsing. This just shows the 63 different columns, and you can see 1, 2, and 3, the group registration ID, district, and date of death does not change. However, you can see rows or data fields 4 to 10, the place of death has been extracted out. to include house number, street, district, county, city, latitude, and longitude. And this parsing expanded it out to 63 different columns. Upon inspection of the data collected from the hackathon and after the parsing, we now had 63 different rows, and we could, on inspection of the data, you can see that Excel allowed for incomplete and incorrect data entries. So data errors within collected data, these needed to be identified, and a method for determining the type of error had to be identified. So was it user input error? Were there missing errors? Was it correlation errors? So through constant consultation between DVD and the computer science project members, the ad hoc parser was extended. As it was built in Java using object-oriented architecture, we were actually able to import new modules to extend our parser. Project logic was built to determine the type of errors for each individual 63 data field. So logic was developed for each individual field to determine what should be in such a data field. Rectification of errors through programming logic was applied where applicable, such as date formatting. And for all other errors, highlighting was done for the DVD members to rectify. We can see these error types here that were identified. So we had input errors, so user input data that does not match constraints set by historians. So you can see on the right, these were identified as red. These were highlighted red. So a group registration, they use numeric, and then you had alphanumeric characters. This would be highlighted as an error. Missing data would be empty fields due to incomplete records, user's inability to transcribe data, or user error, and these was highlighted yellow. And correlation errors would be data that's syntactically valid but semantically incoherent when compared to related data fields. As you can see, it's highlighted blue, where the sex was male and the civil status was spinster, which would be a single female at the time. This would be a correlation record in the whole record, even though it would in fact be syntactically correct. So these are the three types of errors we identified, and we're going to highlight if they could not be programmatically resolved. Results of our error categorization shows that user input errors read occurred on average 2.78% per data set, with a minimum of 1.75 and a maximum of 5%. While 2.78% per data set does not seem a lot, it's actually over 1,000 input errors per data set. And this, in red, we determined these were the worst type of errors as they actually introduced false data into our data set, which could interrupt future knowledge acquisition. So these were highlighted red and had to be rectified immediately by DVD Ireland members. Missing data yellow occurred on average 38.1% per data set. This is a relatively high value, although it should be noted that the expansion from 24 to 63 fields left a lot of fields empty that would be deemed important in the future, so this is the reason for such a high. And correlation errors blue occurred on average 0.01% per data set. So very, very rare, and would be easily rectified. We even had some with 0%. The model-driven approach. So for a web application, we use a low-code integrated modeling environment called DIME. So this allowed the introduction of service integration blocks which would have Java code inside them. And we can combine all of these in a modeling environment to develop a historical web application. So it's Java EE, so enterprise. So for each individual forms, we had general, deceased, informed, and registration forms. A separate page was developed where users could input the data fields where required. And in the back end, instead of using Excel, upon saving a form, it would go back to a relational database, which at the moment was Postgres. So the code is generated from the rich models, produces a web application which users can then input the data into, with individual forms created for each. DIME is built on top of the Cinco platform. ADD-lib classifiers. These are developed in the ADD-lib, in which we have predicates, which are then composed into binary decision diagrams, which these decision diagrams are then composed into classifiers, and we have a classifier for each individual page on the historical web application. These classifiers are then compiled to generate Java code in which reduced ordered binary decision diagrams are then automatically generated. You can see on the right hand side the model of these ROBDDs for the 4 different classifiers. You can see a large memory space. However, computationally they run linearly as each predicate is only processed at most once. The logic is held within each predicate, and the computer programmer programs this logic beforehand, which allows domain experts to compose the classifiers and BDDs themselves, and this is the degree of separation which is required. Java code generation. On composition of the 4 classifiers and ROBDDs, the Java code for the model underneath is automatically generated, and this can be embedded in the DIME historical web application as another SIB, a service integrated block. We can also use this code as part of a Java application to see how our classifier is working on the Excel data, of which you can see on the right hand side in the GUI. This is one of the main advantages of the ADDlib, is the code generation and the ability to take code from one modeling environment and plug it into another modeling environment. So the results of our classification, it should be noted that dataset 8 is deemed anomalous due to a lack of data, therefore is not included in the average calculations, as only 6 of the 24 data fields was input. So our averages are taken across 11 datasets, and we can see that the general form has a 99% pass rate. However, it only has 2 data fields with 2 predicates and 1 BDD, and these were relatively uncomplex data fields with low variance. The deceased form has only 5.89% pass average, however it's composed of 48 of the 63 fields, which comprise 72 different predicates, which require 14 BDDs. So this is a high level of complexity, and it was taken as an atomic, so if any of the BDDs failed, it all failed. So only 5.89% passed all 14 BDD checks. The formal form had 20%, the registration form had 36.81%. Again, registration form only had 2 data fields with 2 predicates, however, the data fields were more complex than the general form. In conclusions, from a computational archival science point of view, we can see that dealing with large amounts of data in terms of Excel spreadsheets is not ideal. It is arduous and time consuming and is not suitable for handling scientific data. For qualitative findings to be discovered by researchers require availability of high quality, verified and complete data sets, preferably in a robust environment such as a database, which can be queried at will. Regarding the DVD Ireland project, Excel spreadsheets cannot be deemed a meaningful resource which researchers can aggregate desired knowledge. Machine transcription is not always applicable, as we saw with the transcribers software. However, new research techniques may provide an avenue moving forward through the use of CNNs, in particular perhaps the joining of the 2 projects with the handwriting, text recognition and the individual letter transcription. However, dedicated resources are required for this. Model-driven development allows for the building of web-based systems that provide the necessary constraints to ensure a high level of data quality. We saw this with the DIME infrastructure as well as the ADDlib. It allows for the inclusion of new techniques when required through service integrated blocks. So you can see that we could generate Java code and we can introduce them, so new functionality, into our model-driven environment through the service integrated blocks. So we can continually extend the functionality of our framework. Future work, DVD Ireland members continue to rectify errors in data collected to date. This is, as we said, a time-consuming and arduous process, which you have to go through over 1,000 read errors per data set, as well as determining valuable missing data and inputting that. ADDlib classifier has to be integrated into the DIME Historian web application as a SIP. So we've generated the Java code, we've extracted it, we just have to integrate it now. We have to determine hosting for our web application and databases moving forward, as well as the creation of a web-based digital humanities platform for researchers and public access. So for a meaningful platform, an end-to-end platform in which we have high quality data that can be queried using different machine learning algorithms at ease without the need for computer science knowledge actually in the domain specific languages. And from a machine learning perspective, we may pursue machine transcription, as we declared earlier, with the 2 new techniques, perhaps a combination of this as well as using transfer learning and historical knowledge discovery through the additional data fields that we have used. These are the references for just within our slides. So thank you. Any questions?